All right, welcome to the first video of Unit 2A for AP Physics 1. So first thing we're going to talk about in this unit video is vector math. This is something we've covered in some detail in previous lessons, but we're going to deal with it a little bit more in depth. So as a reminder, a couple of things that are vectors so far in physics would be position, displacement, velocity, and acceleration. In this unit, we're going to add a brand new thing to that list, which is force. A force is a vector quantity. So what it means is that all of these things have two components. They have both a magnitude, that is an amount. So how much of the stuff? Okay, if you're really confused about magnitude, magnitude is the absolute value of the vector. So if it's negative 20 meters per second, then magnitude is the 20 meters per second. We take off the negative sign. For different physical things, it could represent maybe other physical things. So for example, velocity, the magnitude portion of velocity is speed, because speed is just how fast am I going. The magnitude of velocity is just how fast am I going, not which way am I going. But a vector has magnitude and direction. That typically looks like a positive or negative if we're talking about one-dimensional motion. So if I'm going horizontally, I might be going in a positive direction or a negative direction. That's to the right or to the left. If I'm, let's say, traveling in the vertical, that could be up and down. When we get into two-dimensional vectors, we're typically going to describe direction instead of positive and negative with an angle. Right? We're going to say it's at 30 degrees above the horizontal. That tells me positive or negative in both the horizontal and vertical, and it tells me how much of it is horizontal, how much of it is vertical. So direction can be given as just positive or negative in one-dimensional motion, or in two-dimensional motion, it'll likely be given as an angle. So these are the two parts that are in a vector. That means we have a lot of ways to describe vectors. So here are three main ways that we can describe a vector. An arrow. Arrow has its length as its magnitude. And obviously the direction of the arrow is its direction. So by just drawing an arrow, I've given you a vector. Whatever this is, maybe it's the position of an object. The object's located here, so from some origin point, the position of this object is up and right by a magnitude of whatever this is. I could go get a meter stick and figure out exactly what that distance is. A lot of time when giving arrows in AP Physics, we're going to actually get some more information. So they might tell us this side is 3 and this side is 4. And then we'd be able to be a lot more specific when we get into the trig of it all. That's an arrow. The other form that we are given is standard form. Just like the arrow form, we are again given a magnitude and direction. So for example, 20 meters at 30 degrees above the x-axis. We'll say the positive x direction. So that would look like this person has walked 20 meters at 30 degrees above the positive x direction. I could even then switch that into an arrow. I know it's 20 meters long and at an angle of 30 degrees. That's standard form. It again comes with the magnitude and the direction. So both of these, typically the arrow and the standard form, are going to give you the magnitude and direction. Notice in this arrow though, when I gave you information about it, I gave you actually not the magnitude and direction, I gave the components, the horizontal and the vertical. So for the arrow, it could either give magnitude and direction in standard form, or it could give us what we call component form. That would be the actual x and y components. So if I'm talking about a velocity, that might look like Vx and Vy. If I'm talking about a position, that could be x and y. Depends on what we're talking about. So the one thing we have to be able to do when we're given vectors, since things happen, come on, just drop it off over there. Since things happen in vector form for things like position, velocity, acceleration, and now force, we need to be able to go between these forms. So we're going to be able to move between the forms. We learned this pretty quickly in the middle of the last unit when we started talking about projectiles, but let's make sure we've all gone to trig land and we understand how to do this. So let's take an example where we're given standard form and we want to turn it into component form. So I'm told that I kicked the football at 20 meters per second at an angle of 30 degrees above the horizontal. Now, I probably told you to go ahead and memorize that sine is the vertical component and cosine is the horizontal component, which worked in the projectile unit because they gave us all the angles in reference to the horizontal. But we're going a little bit further into our trig, a little bit further into vectors, and they might not give us the angle in respect to the horizontal. So let's actually make sure we know how to do this. What I'm going to do is I'm going to sketch a triangle. So the 20 meters per second is the hypotenuse of the triangle, and that angle is with the horizontal. So this is me sketching a right triangle to try and figure out what my components are. This is probably something I'm going to start doing every time I have an angle and a magnitude given to me. So now I actually have to think about the trig of it all. This would be my horizontal component, Vx in this case, since we were given a velocity. And this would be my vertical component, Vy. So I actually have to think through the trig, right? So I know that this is my hypotenuse, this would be my adjacent, and this would be my opposite side. I learned this in geometry and again in pre-cal. I went and learned that sine is opposite over hypotenuse. I learned that cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Using the correct trig function, I can find my correct component. So if I want to find the horizontal component, I actually am going to think, okay, well, I have the adjacent side and I know the hypotenuse. So that means I'm not going to use sine. I'm not going to use tangent. I'm going to use the one that has cosine because it has adjacent and hypotenuse. Then I'm actually going to solve this. If I want to find that adjacent side, I'm going to multiply hypotenuse on both sides and get this. For our application here, that looks like Vx is equal to V cosine theta, where velocity is 20 and my angle is 30 degrees. This is how I actually go and find that component. I don't necessarily get to memorize sine and cosine because they can change, right? I actually have to be able to do the trig to figure it out. So I always first sketch a right triangle. Then I label the sides. I choose a trig function and I solve. Now, this is something you're going to do really frequently, so you're probably going to get these memorized pretty quick, or at least get this process down into maybe less steps. You might not sketch everything out, but there will be a test question or an AP test question that gets hard, and they give you an angle and you're not sure about it. You have to be practiced at actually doing this so that you can figure it out when the time comes. Okay, so let's try one that's a little bit weirder. So we're about to talk about forces. Let's say I have a chandelier. I'm bad at drawing, so this is my chandelier. It's like a weird modern art chandelier. And it's hanging at an angle theta from this vertical. So it's hanging up this way. Maybe it has another cord going this way to the wall. This will be the wall. But this is some weird modern art thing. This chandelier is hanging at an angle away from the vertical on this ceiling and wall situation here. So I would need to know, let's say this is a force of tension going this way. We'll call it Ft as I sketch this scenario. And my angle is here. If I needed to know the horizontal and vertical components of Ft, I'm going to follow the steps I just laid out. I'm going to sketch my right triangle. I'm going to label my sides. This is where the angle is, so now this side is the adjacent, and this side would be the opposite, right? Opposite is actually the side opposite the angle. When I am labeling these, I always think about finding adjacent first. I know which one my hypotenuse is. It doesn't touch the 90-degree angle. Then whatever angle that I have, the side it's touching is my adjacent side, the other side is the opposite. So I kind of find opposite last. All right, once I have this, then I can say, okay, well, adjacent and hypotenuse will be cosine, and opposite and hypotenuse will be sine. So notice in that example, I went ahead and skipped actually solving the trig function out. I kind of just jumped to the conclusion, all right, that's my adjacent, that's my opposite. You do have to be able to write this out and draw it. So this is something to remember. Putting component forms back together again, not really something we have to do a ton. We saw this last, so just as a reminder, it's a right triangle. If you have an X and a Y component of that right triangle and you're looking for the total, so this is R, maybe for radius, right? How far am I away from some origin position? My radius away. Well, to find the side of the hypotenuse, R would be the square root of x squared plus y squared, just using Pythagorean theorem. To find an angle, I would set up tangent. I'm going to do an inverse tangent, and it will always be the opposite side over the adjacent. So typically, that's y over x, because we really always write our answers in reference to the horizontal direction. All of our answer angles are referencing that horizontal. But read the question if for some reason they're like, no, what is it close to the vertical? Okay, well, this is now my angle. How would that change this equation? Okay? So that's the trig that we need to know for vectors. One thing we didn't do for vectors, right, last time around was add them together. We kind of did this a little bit with relative motion, but all the vectors were in one dimension. So now we're going to say what happens if I have a vector A and a vector B, and I want to add them together. One thing to note, whenever we're talking about vectors, you might see this symbol. When I'm doing problems on the board, I oftentimes don't write it because I'm trying to move fast and get this information in your heads. But that symbol stands for vector. So when I put that little hat symbol on top, it's kind of like an arrow. It signifies vector. So when we're doing a vector addition, you always want to remember two things. First, you put the tail of the second vector on the tip of the first vector. That's how we add them together. We call it tip to tail. So if I have A and B here and I want to add them together, I'm going to sketch this over here. I would genuinely add them together. So I put the tip of the first vector to the tail of the second vector. Second thing I have to do, draw the resultant vector from tail of the first to tip of the second. So that means I'm going to sketch it from the tail of A to the tip of B. And this dashed line is my resultant vector. And that's it. Most likely they're going to give you some amount of numbers here, right? They're going to somehow tell you about the magnitude of A and the magnitude of B and get you to get a number for this. So for example, if I told you A was 3 tall and it goes to the right 4, B is going to the right 2 and goes down, let's say 2, maybe not drawn to scale, that's okay. How would I actually do this math? Well, I just add the components. So if AX plus BX, that'll be my X component of the total, and AY plus BY equals my Y component of the total. So in this case, AX is 4. It's this component 4. BX is 2, so my total would be 6. In the Y direction, A is 3. B went down, so it's a -2. So I get 1. So my resultant vector goes in the horizontal direction 6 and goes up 1. So I could add that together. Using that math we just saw, I could put that into a magnitude and direction using Pythagorean theorem and trig. What if I'm subtracting? Oh no, what if I'm subtracting? What if I want to do A minus B? Simple, we follow all the same steps. All we're going to do is take B and flip it around. So A stays the exact same. And B we're going to flip. So it's currently going down and to the right. So now it's going to flip and go up and to the left. So that would be -B. And we still add them together. So vector subtraction isn't scarier than vector addition. You're just going to flip one of the vectors. Okay? When it comes to vector math, adding and subtracting them, you're always either drawing a picture or, most likely, adding or subtracting components, right? If we go back, remember, A had a component horizontally of 4, vertically of 3. B was vertically 2 and 2. So if I want to do the subtraction, AX minus BX would be 4 minus 2, so 2. AY minus BY would equal 3 minus a -2, so 5. So for vector addition and subtraction, maybe they're going to ask you to draw some vectors. We have arrows out here. We're going to learn how to draw them. We follow this technique, tip to tail, and then draw the resultant, that's the combined vector, from the tip of the first, or sorry, the tail of the first to the tip of the second. Most likely you're just going to find the components and add them or subtract them. All right, that's vector math. Last thing we're going to talk about is center of mass. To understand why we need to know the center of mass, let's talk about particle theory. Particle theory means that in reality, if I want to talk about this tennis ball, I am not going to talk about the forces on the tennis ball. When I talk about it moving, and I say its initial location is here and its final location is over here, I'm talking about this whole object, right? I'm not talking about the whole ball, right? Because technically, right, there's about a 4 centimeter difference between the front end of the ball and the back end of the ball. So when I talk about its displacement, right, I have to be careful. Am I talking about the front of the ball or the back of the ball? Because how far those have moved changes. If I measure from the front and then to the back, its displacement will be different. So objects get tricky if they're big, if they have size. So we don't want them to. The easiest way to deal with objects, especially now that we're getting into forces, and you might have the question of, okay, well, when I hit this tennis ball with my racket, am I hitting this side? Am I hitting this side? Am I hitting that side? Right? You're like, shouldn't it matter? Well, it doesn't, because we treat all of our objects, for the most part, as long as treating them like this doesn't change the outcome, as particles. We teach this as just a single dot, not even this size, just a single dot at its center of mass with its mass. So even though the tennis ball is all around here, as we do our physics problems, we only look at its exact center of mass. So center of mass is pretty easy. If it's a solid object that has roughly the same density throughout, I can expect the center of mass to be directly in the center, right? If I get objects that maybe aren't so organized, right? This one is flat at this end and curved at this end, but it's pretty much the same thing, right? All throughout. So I would expect the center of mass to be roughly in the center of this calculator. Let's see what else I have on my desk. Ooh, what about this calculator? This one gets a little bit narrower at this end. So since it's a little narrower at this end, I would expect the center of mass to be skewed a little bit further over to this end because it's thicker, right? A little bit thicker over at this end. Just using what I have on my desk at this point. It's pretty much all the cool stuff I have on my desk. Yeah, that's pretty much it. Everything else I have is really like evenly distributed. So let's talk about some other objects that I can draw. I don't have access to, but I can draw. So let's talk about maybe a baseball bat. That's a baseball bat. So a baseball bat is thin on one end and thick on the other end. So I would expect its center of mass to sit closer to the thick end, right? And that for an object is pretty much it. It's either uniform density, or for AP Physics 1, we can pretty much tell which way it would be skewed, right? Where there's more mass, so the thicker side, right, is going to be where I have more of my mass, and therefore the center of mass will be skewed that direction. Another example I could do would be, I don't know, a pickleball racket. Kind of looks like that. I would expect the center of the mass of the pickleball racket to be kind of skewed up into the center of the paddle versus down in the handle. So those are some examples. But what if I need to calculate it actually for a system of objects? Maybe I have a system of objects that are all moving around together. So I'm going to draw these as big dots. And I want to know what the center of mass of the system is. Maybe my first dot is 1 kilogram, my second dot is 2 kilograms, and my third dot is 3 kilograms. I want to find the center of mass for this system. It's not a single object, but I want to treat it like a single object. I can still use particle theory to do that. I can treat, again, as long as it doesn't change the physics of what I'm doing, I can treat this system of 3 objects as a single object at its center of mass. But where is its center of mass? Which way would it be skewed? This is 1 kilogram, 2 kilograms, 3 kilograms. So I would expect my center of mass to be skewed this direction, right? It's probably sitting somewhere between 2 and 3 kilograms. Good news is we don't have to guess. If we have a system of masses like this and we know what they are and we know where they're located, so I'm going to say that this is my 0. This one is located 0.25 meters away. This one's located 0.5 meters away. And this one is located 0.75 meters away. We can calculate it. We have an equation for center of mass, xcm. It is a vector because it's a position, is equal to the sum of each mass times its position. So they put i's here. That just means I don't know how many pieces I'm going to have. This is a system of 3. I could have 4, 5, 100, 1,000,000, right? It could go up. So it's the sum of the masses times their positions over the sum of their masses. Kind of like a weighted average is pretty much what this is. So let's do this. This is what the equation looks like on the sheet, the formula chart. In practice, it's going to look like this. M1 x1 over M1 plus M2 x2 M2 plus M3, ooh, that's a 3, x, that's a weird x, sorry about that, plus M3. Got a little wonky at the end there, not really sure. So let's calculate it. xcm is going to be equal to, I have my first mass, it's 1 kilogram at a position of 0.25. I like to go ahead and add the masses on the bottom as I put them on the top. My next mass is 2 kilograms at 0.5. My third mass is 3 kilograms at 0.75. So on the top, it's a sum of all of the masses times their respective locations. On the bottom, it's the masses, right? All added together. So let's do the math. I get 0.25 plus 1 plus 2.25 all over 6. That would be what? 2.5, 3.5 divided by 6. I don't know what that is off. I mean, I could do it, but I don't want to. 0.583. Which is located right here-ish, somewhere around there. And that would be the center of mass of the system. Let's do one more example. What if, instead of just 3 separate objects, they are actually connected? I'm going to fix this because it's bothering me. M3, X3, M3. Oh, I did it again. I'm trying to draw an X, that's why. So I have a piece of wood, we'll call it a plank. I have one person standing on this end. I have one person standing on this end. So this person is located, I'm going to move my 0 to right at the end of my plank. And I'm going to say this person is located 2 meters away. This person is located 18 meters away. This guy is 60 kilograms. This guy is 20 kilograms. But my plank has a mass. It's an actual plank. My plank has a mass of 45 kilograms and a length of 25 meters. One thing that's important to note that I didn't say before the last example, I have to determine my reference point before I start this. In order to finish this equation, I have to be able to put a position next to each mass. To know that position, I have to know what I'm calling a zero position. So in the last example, I set it to the left end of all of those masses. In this case, I'm talking about the left end of the plank. I typically choose the left end because right is positive for me in this case, and right is typically positive. You could change that. I don't recommend setting it in the center, but you could do it if you wanted to. It's up to you. But I'm going to reference all of my locations from this 0 meters right here. So, no. XCM is equal to, I have 20 kilograms, that must be a child, located at 2 meters. I have 60 kilograms located at 18 meters. And I have this plank. So the plank is 45 kilograms, but where is it located? Well, we talked about a uniformly dense object is going to have its center of mass in its center. So the center of mass of this plank, we're going to treat as a particle located right there in the middle at 12.5 meters. If I put my masses in, I've got 20 plus 60 plus 45. So in this case, I get, oh, I'm not doing that math. Here I go to my calculator. 20 times 2 plus 60 times 18 plus 45 times 12.5. Divided by 20, 60, and 45. So at 13.46 meters. And that is center of mass. They could make these be in both the x and y directions, so I could have things located horizontally away from each other and vertically away from each other. Just like everything else we do in 2 dimensions, we're going to split and find the position in the x and the position in the y. All right, see you in class.